So we're back, continuing on with the stock assessment section. Whenever you're ready.
Okay, maybe I'll just check and see if there are any questions that popped up related to data sets, inputs, before I continue on to the modeling. We can, of course, get back to anything later on in the presentation as well.
I have one that's puzzled me for a while. I was going to bring it up when you show the size of the age plots. Oh, it's right there. But using empirical weighted age, of course, the empirical weighted age is biased. So you selected faster moving individuals. So, and I've never, I'm thinking about it for a long time. Never got around to like seeing which it matters. Yeah, but it depends how you use it too. If you use it to convert catch to catch at age, that's fine because that's the right way to use. But if you then say, well, that's the weighted age for a spawning stock biomass, it really isn't biased. Selectivity, and I think the variance. Something that
Good points. I'll tell you the things that we've thought through as we've thought about how to use that. So I totally agree that from first principles, it's a product of sampling. So any bias in the sampling, say a length-based selectivity curve, would create a bias in the observed length and therefore weight age, particularly for ages where selectivity is. The ways in which we deal with that. So we don't tend to see many fish less than 5 to 7 years old in a survey. And so what we do is we use the trawl survey data to piece in the younger ages. And we use, and then that gets spliced together with the rest of the survey to get a population age. The way we've thought about it is you'd be in a bad spot if you were trying to take, say, fishery weighted age, where the fishery caught a lot of old fish, apply it to create spawning biomass at age. If your maturity ogive was, say, to the left of fisheries. But in this case, we feel like the maturity ogive is close to or even to the right of where the survey selectivity is. So we use the survey to generate the age for spawning biomass. There's not a lot of spawning biomass at those ages where biased. And also using the trawl survey, which does select small fish to splice that in. And then, of course, for the fishery, we're using the direct AC fishery, which is just to use because it just is what it is. Whatever the bias is, it's the accurate thing.
That sounds reasonable, but trawl survey is also not very expensive.
We combine the Gulf and the Bering Sea. It's just a naive. We just pull it all, combine it. Honestly, there's not a lot of variation for the sizes of fish that matter. It's coming from the trawl survey, but it's certainly a consideration. It is, I think, by far the lesser evil of that versus dealing with the growth function. Growth function is horrific. I'm pretty sure I have a picture of that coming up. It's both linear and huge.
Selectivity assessment on it.
I'll get to that. Yeah, it depends. For the most part, yes, but in the areas as fleets models, we allow some areas to be no-shaped. All the models have at least one or two fleets. Yeah, so maybe we look at some results and come back to that. So I'm going to walk through now the modeling sections of this presentation. I need to be meaningful. There we go. Just have the ability to. Seem to have.
So your percentage. This one if you need to. I'm not fortunate to make him. Thanks.
Yeah, for some reason I don't seem to have capability on my computer, so I'll just use them. Just go on the screen. Okay, so as you will recall for Pacific Halibut, we have been for a number of years, I guess more than a decade. Sorry, I'm still working on a few technical considerations. I still don't have direct access. It's okay, I can use the mouse. For over a decade now, we've been using an ensemble of 4 individual stock assessment models to assess the Pacific halibut stock each year. And these models represent a two-way cross between time series length and structure of the fleets in the model. This is 4 different ways to aggregate the data. And each of these models has shown different performance over time. We see this is actually the results of this year's preliminary assessment. You see that the short areas as fleets model is the largest estimate of biomass throughout the time series, although they're all giving a pretty similar trend overall, including that little bump in the around 2016, which corresponds to the maturity of the 2005 year class at 10, 11, 12 years old. Alan and I, a few years ago, I guess 7 years ago now, did an analysis looking at the stability properties of using an ensemble versus using a single assessment model. And wow, creatively found out that the central limit theorem applies to a sample of 4. If you take the average of 4 random variables that have some year-to-year variability, it's more stable than any one of those variables was underneath. Pretty groundbreaking
job,
stuff
guys.
there. It was published, so it couldn't have been that boring. But I guess the point is that I can say I've personally seen over the years, there'll be one model that's on the low end or the high end, and then a year or 2 later with some new data and some updates of things, and it might be a different model that's on top. Generally, the coastwide short model tends to be the lowest estimate of biomass, and the areas as fleets short model tends to be the highest estimate of biomass, I would say on average over the last decade, but they do bounce around somewhat. And I think the important thing for our purposes, we present the commission with our results in the form of a decision table every year. And that's where I think using an ensemble is important, because although of course it doesn't capture all of the uncertainty, if you look at the distribution of these estimates in the bottom left here, any one of these models wouldn't do a very good job of reflecting the uncertainty that we have in the problem in general, which is the full assessment. We just picked one of those and we created a decision table. It wouldn't span the full range of concern. So that's really we get out of a 4 model approach. We get well, one, we don't have to make an arbitrary choice among these models, which most places you could just pick one of these 4. And I can show you an example from regions of the U.S. where they love their coastwide models, or they love their areas as fleets models, and other places where they love their long time series models, and other places where they like nice short contained models. Let's go West Coast, Northeast, West Coast. And so it gets us out of that box, which we kind of hope in the long run also takes away a little bit of the analyst effect. I know when I came here, I kind of had my favorite way of setting up a stock assessment. If you told me I could only build one model, it would probably have looked a lot like the long coastwide model, maybe the long areas as fleets model, depending. But the idea is this is a legitimate point of uncertainty. And I think what we're striving for in each of these models is not to find the truth. It's to have each model be internally consistent and to reflect a series of hypotheses about how the stock works and what might be the best way to approximate those dynamics of a stock assessment. All these models are wrong. All stock assessment models are, but they are different ways to approximate the very complicated underlying purposes. So that's the rationale for an ensemble versus a single system. Spend more time on that if you want, but we don't have to. As I mentioned, it's a 2x2 cross. The short models start in 1992, and we choose 1992 because 1993 is the first year in which we have a geostatistical model and a full survey index for the coast. So basically, 1992 is the beginning year when we have square data sets across all the sources. We have all sources of mortality. We have comprehensive survey. We have all the fishery. It's in many places, you'd look at your data sets and you'd say, well, this is the first year we can really create a rock solid model. So we'll start there. The long time series models go all the way back, and they take the other approach, which is let's figure out when the mortality started to actually probably appreciably affect the dynamics. Let's start the model there, and let's just let the data accumulate as it does. And another way to think about this is you can look at the early part of the time series and the long time series models as essentially a burn-in period to get us to the data, reflecting all the information that we have on the way, so that when we get there, we're entering the data streams with the combined information that we have, such as it is, and then fitting them.
Can you just mention the initial conditions for both the short and long?
I can. I'm trying to recall if I have a better slide to do this. This might as well do it now, although I may touch back to it later. So in the long time series models, we assume that they start in equilibrium with recruitment deviations prior to the first year of actual data. So there you basically just do have a burn in, and catch is assumed to be 0 before 1888. It's not. There's evidence that the Makah tribe in Washington were catching over 1 million pounds of halibut in the late 1800s with traditional methods. Yeah. Yeah. They had a substantial halibut fishery there. They still do today, but geographically quite localized. So they have been harvesting halibut since time immemorial, and as have other tribes on the coast. And so there is certainly some level of harvest prior to that. But in terms of industrial fisheries, there's really no much prior to that time period. So that's essentially using time to not have to worry about initial conditions. The short time series models, however, are important because we know there's 100 years of catch before we get to the start of the model. So in those cases, we estimate not only recruitment deviations for n ages -1 at the beginning of the model. So basically everything except the plus group has a deviation associated with it. And then for the plus group, we use in synthesis, it's set up as an environmental offset, but basically it allows R0 to be whatever it needs to be to fill the plus group with the right amount of fish to match the data. So it's essentially a fully free vector of numbers at age in year 1 of these short time series models. So there's no assumption that they're starting in any kind of an equilibrium. Just start with whatever numbers at age they need to have to enter the data. So yeah, good point. Did quite different approaches there. I've already gone through the rest of that rationale, so I'll continue on. Two versions. Okay, so the basic structural assumptions, as I mentioned earlier, these are age-based models using an empirical weighted age. And the reason we use empirical weighted age is that plot on the right here. That's the growth curves from the fishery independent setline survey data for females and males. And you can see that we've got data down to roughly age 4. And there's very little evidence, maybe more so for males, but for females, there's not much evidence of on birth land They basically are linear, grow linearly. And whatever trajectory that fish gets on, it just stays on that the rest of its life. The older it gets, the bigger it gets. We've done some looking at individual cohorts, and there's some evidence that if they get off to a good start, they stay on that track for the rest of their life, even though Joseph has shown that they have the ability to show compensatory growth in laboratory conditions, where if they're stunted due to lack of food or temperature, and then they're warmed up and fed, they can catch up. We don't see that in terms of cohort factors. We see that once they're behind, that cohort seems to stay behind the rest of its life. For a few years, I did work on building a model that was, I would call a growth process stock assessment model. We had a growth relationship, a growth curve in the model, and we could then fit length frequency data in addition to age data. And I discovered two things. One, with this amount of variability, the CVs of length at age were massive. So the length data gave you almost no information about the age data. So it imparted almost nothing to the problem, but it took an incredible amount of technical overhead to do, because not only did you have to model the growth curve, but you had to model time varying growth. There's the curve on the left shows you the difference in weight at age, and length at age isn't as variable, obviously, because weight is a cubic function of length roughly. So there's less variability in length, but there's still a lot of variability in length over time. So we ended up having to model time varying length with huge CVs in order to accommodate length data that was telling us basically nothing about age. And so we gave up.
Is that just all your data pooled in one?
Yes.
Just so these big swings in size at age are represented. So that's one source of variability.
Well, actually, but those are survey data, so that's only from basically 2000 onward. So if we had the full-time series, it'd be even worse. Yeah.
It would all, I mean, it would be nice to see like some kind of distribution on that thing to see, like, because you can't tell. The whole center of that thing could be where all the points are, and the rest is just covered with other stuff. But I agree with you.
I'm just providing this as a measure. It's not intended to be in specs. We can certainly produce
Some kind of set,
sure.
like envelope with some distributional information on those things to see if there's any. It certainly looks like the top part has a nice curve to it, bottom doesn't, on both of them.
Yep.
And with some of the other station like that I've ever seen.
It is. I remember when I first started, Steve Martell was here, and he was fitting a growth curve. I heard him exclaim several things I can't repeat from his office. And he came over because he had literally, with Carl Walters, just written the book on how to do this sort of thing. And he was applying something they had just done to a whole bunch of species, and it absolutely failed on him. And this is definitely not a von Bertalanffy curve. I think actually he did some analysis looking at fitting several different growth models. The Richards growth model, von Bertalanffy, and even another even more flexible one. And I think linear growth was about as good as anything in this data. It was pretty close to linear, especially for females.
And usually that's something you see aging here.
I don't think so, because our ages are actually more precise than most fish. I mean, there is aging error in here, but it's not, we're not misaging that 18-year-old fish that's the biggest fish in the female data set. That fish shouldn't be 40. There's no question that it was somewhere between 15 and 20.
Yeah. It's not like scale-based data. It's pretty long season. It's like,
Exactly.
well, you don't, actually the scale-based ages aren't this ugly. These pressed, so you get the, but the lower ages, it's variable.
So this is the basic rationale for going with an empirical weighted age model versus a growth process type model. What it does mean, an important consideration though, is that because we have a minimum size limit, and because there probably are some length-based selectivity aspects, it means that we have to deal with time-varying selectivity. Because those two things interacting with time-varying growth means that the selectivity at age has to be time-varying. there's no way around that. So we have to deal with a time varying aspect of selectivity. And that's the cost of bypassing dealing with growth, is that now we have to deal with time varying selectivity. So the way we parameterize these models, they're all set up on a Beverton and Holt stock recruitment relationship. We don't have any thinking that a record ought to be more appropriate. And as you'll see, the stock recruit relationship, because we estimate and tune the recruitment deviations, the form of the stock recruit relationship actually doesn't have much of an effect on the estimated annual recruitments. They are flexible enough to get us the recruitment we need to match the age. We do estimate annual recruitment deviations from, as I mentioned, the beginning of these models, even the initial age structure through the forecast period. So recruitment variability is propagated into any one of these models. We currently fix steepness at 0.75. I'll show you some sensitivities later to that. That's loosely based on Ram-Meyer's meta-analysis suggesting that for flat fish, somewhere in the 7 to 0.8 range is generally appropriate. We haven't found any evidence to suggest otherwise. When we try to estimate steepness, the data sets are all consistent with effectively very little stock relationship, steepness closer to 1, if not equal to 1. And that's because we tend to see these decadal swings that seem to be caused by external or extrinsic rather than intrinsic stock functions. However, we think it's wise to have a stock recruit relationship in the model because we know the origin is a real point, and that provides some level of assurance that we are not just going to be, especially in forecast setting, we're not just going to be projecting recruitments that are completely unlinked from spawning biomass. If the spawning biomass goes down, we would expect a priori some reduction. So that's captured here.
Was Sigma R constrained at all?
Sigma R is tuned, and I'll show you the tuning algorithm. But basically, we find the Sigma R that's consistent with the degree of variability that we estimate in their recruitment deviations. Show you why that's not biased.
Well, I mean, for this stock assessment, you're only forecasting 3 years. So if you're doing a forecast of recruitment, your best model of recruitment is like the year before, right? There's the time series effect of, like you were showing, the PDO was really driving stuff, right? It's super low right now. So spawning biomass, whether it's low or high, that's going to be the dominant feature. So when we do short-term projections, we almost never use the stock recruitment relationship. We just pull an autocorrelated series off the last, so that you don't immediately go from, oh, we're at a negative 2.5 deviation in the most recent estimate back to the stock recruit relationship. Got it. You can only kind of ease your way back up there. I mean, it's artificial, but it's probably the most realistic way of doing it.
And so that's exactly why we limit our projections to 3 years, because those fish, we have data starting at ages 4 or 5. And so that means that we don't have the spawning biomass time series is essentially independent of any stock assumption. So at the end of 3 years, in the 4th year, the first recruitment that we don't have any data on would start to mature.
Right.
And that's why we stop at 3, because we don't want exactly that.
So you don't really need this. You don't really need this. Because then you got to put a briar on it.
Perhaps not. It does feed into the dynamic unfished spawning biomass calculation, because it allows us to correct for the recruitment deviations. It allows us to estimate that we would have had more fish if we weren't fishing than if we were fishing. So that's the one place that it does feed it. And that's actually not part of the assessment. That's part of the reference calculations. It has no effect on that. the time series. It's just when we count.
And I mean, you do need it for the MSE as well.
We do need it there.
Yeah, that's, yeah, I think your point is valid for the MSE. You see the MSE results jump up pretty quickly.
They should they need to fix that.
Yeah, I mean, we do use the PDO regime as an average recruitment. So if the current regime is negative, we'll continue having lower recruitment. But I think with
Yeah.
halibut, there is a lot of variability from year to year. I don't know. I've never really looked at the correlation in recruitment deviations. But I mean, 1987 came out of nowhere.
Well,
You know,
they
I
do,
think-
they do, but on average, you just look at your time series, you don't see white noise,
Right.
which is what you're assuming if you don't have at least, and it doesn't take a lot. It doesn't take a lot of autocorrelation to not let it snap back to average, because that's what it's snapping back on average.
Yep.
It's not that it can't go, like we see that all the time, right? The next data point is 10 times higher.
Yep.
Which is fine. Just on average, it's going to be more similar to the last few years.
Yeah, for sure.
Have you tried recruitment system around?
Have not. I guess I have some reservations about the degree of autocorrelation observed in recruitment, because I can think of a bunch of different observation processes that would also lead to autocorrelation in estimated recruitment. Length data, aging error, all
Oh,
these
yeah.
things. If not,
For
if
sure.
you don't get those perfect, you're gonna smear recruitments, which makes it
Absolutely.
look auto.
Yeah, definitely. I mean, we just went through this with our shrimp assessment where somebody who knows just enough to be dangerous was like, well, your projected recruitments don't look like the history. Shouldn't. The history is what you just described, and
What you
projecting forward is pure recruitment.
Yep.
But what I'm saying is like, I wouldn't estimate recruitment as an autocorrelated series. Sometimes they don't return anything for the autocorrelation either. But certainly in the projection and in that first however many years it takes. Because it is quite, I've seen it time and time again. It's like, wow, you snap right back. Like we used to look at the Alaska sablefish assessment. It was always like,
Yeah.
the stock's going down. Oh, but the projection always does this. It's like, why does it keep doing that? And it's because in 3 years, it's back on the recruitment curve.
Would you do a similar thing if, in more recent sablefish years where you've had a series of very high recruitments, you continue projecting with more high recruitments then?
Well, that's the nice thing about just taking an autocorrelated recruitment going forward.
But then it
If it's
would
high,
be,
it's going to stay high.
Yeah.
Yeah. If it's low, it's going to stay low. It's just that you're not assuming things are immediately going to return to some average
yeah.
next year.
We project on this.
You project under whatever the PDO regime is that you're in at the time. Yeah, so I guess the takeaway I think from this is that, and you'll see later on, the stock recruit relationship doesn't really have much of an effect on the stock assessment. It's most important in the projections. We cut the tactical projections off at 3 years to avoid electronic recruitments, basically, recruitments that we've never seen before. And I think this is a good case of where we've tried to structure the assessment to help feed into the operating model a little bit, but we can't do everything. And maybe something like estimating the autocorrelation from the assessment to feed into the MSE operating model would be another place that we could cross-link the two.
Especially if you are using a relationship, but sometimes it's simpler. Statistically, it's more robust to just estimate average recruitment and deviations. You have to throw priors on stuff, all that, but we do have that consequence. Average recruitment is usually way higher. The stock is low, right? than what you're gonna get.
Yeah, and it's certainly having an effect on the sea results. That's why they've been very optimistic.
So as I mentioned, the other features of the stock recruit relationship are the initial offset, which is the short models. And again, that's just essentially the magnitude of the plus group in year one is affected by the initial offset. I think Mark Monder actually has a paper reviewing the need to estimate the numbers at age or the folding down the recruitments in year one of a short model, and then the degree of fish in the plus group as a separate parameter. So that's able to be done. And then we have the PDO coefficient. I have a whole slide on how the PDO coefficient works. That's only in the long models. So we don't include the PDO in the short time series models. In those cases, we're just estimating the recruitments, and you can see the same kind of pattern, but we just don't have the long enough time series. We don't even have one cycle of short time series. It's arguably, even with 4 cycles of the PDO in the long models, that's a pretty weak data set to estimate relationship. 3 high points and 2 low points. It's not much to estimate a relationship like that. I think Melissa Haltuck in her dissertation showed that you needed like 500 years of data to estimate a 10 to 20 year regime effect reliably across all different stock data conditions.
In any case, it doesn't look like it's surplus.
We have great age data, so the recruitments are pretty anchored in regardless.
Again and again, that conversation, but we don't have any environmental covariance. So, well, if we had environmental covariance, the recruitments would be estimated the same. It's being estimated through that covariance.
But if we had environmental covariance that could be projected into the future, it would make Alan's job a lot easier in trying to do long-term stock projections and dynamics.
Doesn't make it easier. Just means now I have to model the PDO.
Just right.
Is someone else doing that?
Yeah.
Really?
So we have separate natural mortality for males and females, which makes a lot of sense given the difference in growth and size of those fish. Their males are always estimated. Females are estimated in all models except the short coast. And I'll talk more about that, explorations into that later on when I get to sensitivities.
Which one is higher, males or females?
Well, interestingly, it's complicated. So we used to think that males had a much lower natural mortality rate. Just make sure I get this right. Yeah, much lower natural mortality rate. Then when we got sex-specific information from the fishery, we found a higher proportion of females in the catch than we had historically understood. And so Z for females, to maintain the same Z to fit the data, we ended up with a lower natural mortality rate on females, which made the stock look, brought the males and females a little more into line. As you'll see, all the models estimate a slightly lower male natural mortality rate, but not a lot lower, except the short coastwide model, which actually estimates higher natural mortality rate for males. But that's the one model where females are fixed at 0.5. So the only place where males are estimated to be higher is the place where they're estimated, but the females are not. Because when we tried to estimate it, it just wants to go to a high value. We don't seem to have enough resolution in a single fleet, a single fishery, and a single survey for that short time period to resolve natural mortality. But that said, we don't have a lot of basis for 0.15. That was the big discussion 3 years ago in the 2022 assessment. We found we could pretty reliably estimate it in the areas as fleets, where we have effectively more data, but not coastwide shore.
What is it you estimate?
I'll show you. I got a table. It's between. I'll show you that. And the uncertainty of those values as well. We assume asymptotic fishery and survey selectivity in the coastwide models, and we assume dome selectivity in the areas as fleets models, except in regions 4 and 4. So the east side of the stock, where the fish, where the old fish aren't, are allowed to be dome shaped when we have an areas as fleets approach. Basically, if I were to plot the average age is older as you go to the west side of the state. On the east side of the state. Even though the bigger fish are on the east side of the state, it's because the faster growing fish are on the east side of the state. So size at age is higher on the east, but absolute age tends to be higher in the west. And that's a pattern that's held up over time across a lot of things.
You use size at age by you account for that in the bioregions?
Yes. So in the areas as fleets models are not explicitly spatial. So we still have a coast-wide maturity at age factor. But for the fishery and the survey, we treat each of the data sets as areas as fleets. So it's implicitly spatial.
So you have a fleet,
You have a fleet weighted.
maybe close by.
And then the coast-wide matrix is for maturity. And so that's the weighted average. It's the same matrix that's used in the coast. But the mortality, sources of mortality and the survey expectations are created based on region specific size and age. Okay, so now a little bit about how we allow for time varying selectivity. So this is just showing you a generic male and female selectivity curve, and the way this is parameterized. As I mentioned, we have to have time varying selectivity because we have differences in the areas as fleets models. We have differences in spatial availability, and we also have differences because growth interacts with gear selectivity. We have time varying growth and a minimum size limit. We would expect a priori time varying selectivity at age. So we have an ascending parameter, a parameter that defines the slope of the ascending side, and we have an offset to that for males. Then we have an age that or a parameter that defines the peak of selectivity. And there's an offset to that peak for males as well. Not a vertical offset, but a horizontal. Then there's an offset in the scale of males relative to females. So that's the height of the two curves. And that's allowed to time vary as well. So, but what this allows us to do, this approach, by treating it as offsets, it allows us to propagate time varying selectivity without having to estimate the full matrix of selectivity at age, or even a full vector separately for males and females. We assume that for a given size of fish, that the effect is going to be the same. And so we basically are accounting for growth with the offsets. Time varying components come across in both.
And these are all not confounded.
They're correlated, but yeah, we can estimate those vectors. They're all set up as random walk over time, and the sigma that defines the variability in the random walk is tuned, and I'll show you the algorithm. And then we have dome-shaped selectivity. Obviously, we have 1 to 2 additional parameters to define the shape and degree of dome. And that's for region 2 and region 3 in the areas as fleets.
We have the correlation matrix.
We do, but I don't have it in this presentation. Some of these parameters are in the 85 to 90% correlated. They are heavily correlated. Okay, so this is the tuning process. And this is consistent. This is a method that was developed by Rick Mathot and Ian Taylor quite some time ago. And it's basically, this is the reason why you can't use maximum likelihood to estimate a hierarchical variance parameter. It will always be biased because the point estimate of the deviations is not the integral of the uncertainty in the deviation, it's the point estimate. So that's why you have REML and loss approximation and things like that. In this case, this is a maximum likelihood iterative approach to get to the same result. And it's basically, it is the, and I don't know why my square root disappeared. That line is actually supposed to be square root, sorry. Adobe doesn't like square roots, it likes averages better. In the document, I'm pretty sure it's correct, but basically it's the square root of the sum of the variance of the D's plus the variance among the D's. And so what this accounts for is that you have variance of the estimate of each deviation, but then you also have the variance across. And Rick and Ian showed that they used recruitment as an example, but what they showed is that if you start with a sigma, you estimate the D's, you account for both sources of variance, and then you tune the sigma until these things are roughly equal, you get an unbiased estimate of the variance of those things in an iterative context. It's certainly not as elegant as a random effects model where you just estimate it and you're done with it. That's why I would really like to be moving toward a true state space model where you can just estimate these sigmas as opposed to have to tune them, because this is a royal pain to get through all these. But what I actually find is that they tend to settle out at an internally consistent value pretty quickly. Start them at a fairly large value, and then a couple of tuning iterations, and they settle down. And they are largely independent of the sample size and all the rest of the data stuff, because they are being dictated by how much variance you need to explain the data that you have. So they're closely related, but they're kind of a separate part of the problem. Think about how the model's accounting for this stuff. So we use this approach to deal with any of the time varying components. So the sigmas that we have, again, are not estimated. We're not propagating the uncertainty in the sigmas for the random walks the way we would in a true state space model. But we are generating what should be an unbiased and internally consistent value for those sigmas, rather than just picking it, setting it, forgetting it. Okay, so this is how we treat the PDO. So the PDO is done using a link coefficient. And here I'm showing this as beta, where basically beta is a modifier on, or e to the beta times the PDO, a binary PDO regime, is a modifier on R0. So when the PDO is high, PDO regime is 1, beta affects the R0 parameter in the Stockford relationship, and when PDO is 0, it cancels out, it doesn't. The nice thing about this approach, and I haven't written out the full Beverton and Holt there, but and my function parentheses disappeared as well. Sorry, they're right in the document. Recruitment is a function of the spawning biomass, the R0 prime, which is this R0 modified by the recruitment, unfished B0 steepness, and the bias correction. The thing that I like about this approach is that if I were to put soccer scores instead of the PDO in here, which we know are garbage, I should get an estimate of beta of 0, and this would cancel out. So unlike treating a recruitment covariate as known without error, where if you put the wrong thing in, you get the wrong answer. In this case, if I were to put garbage in here, I should just get a beta coefficient that goes away, and I should get the same stock-recruit relationship I should have if I didn't put it in. So this is what gives me some comfort that it's okay, as long as we continue to see a relationship, it should be okay to take this approach, realizing that we're only adding what the data suggests we should be adding to the stock-recruit function. And I'll show you the values for these coefficients. And like I said, I've been estimating these coefficients for 10 years, and Bill and Steven started in 2001 or 2002, and they seem to be explaining a similar amount of the overall variability in recruitment. Doesn't help at all on annual recruitment variability, but on average, we tend to see higher recruitment when the PDO is positive than when it's negative. So this is a way to capture that.
Do you estimate both unfished biomass, spawning biomass, and earth? So you're deriving
SB0 in this case is derived from steepness and R0 prime and whatever biology. And I'm sorry, the parentheses for the function are missing here. Okay, so I already mentioned this a little bit earlier, but the priors on selectivity for these sources where basically we don't trust the data aren't completely representative of everything we want, or they're a proxy. We put them in to get selectivity, but we downweight them essentially as much as we can and still be able to estimate selectivity. So specifically for non-directed discards or bycatch trawl fisheries, well, not just trawl and longline fisheries that can't retain halibut, we have length sampling that is variable in its coverage. And so those lengths are converted into ages based on trawl survey age length keys. And then those ages then are used as a prior on selectivity. So we put that time series of ages in. The data overview document shows the time series of pseudo age comps for each of these three components that is priors. Then we estimate one time invariant selectivity function. And again, that's downweighted, so it's having little effect on the problem other than to get the selectivity curves for each of these that are basically, we're finding a selectivity that will roughly take out the right age categories. And so the real challenges are we don't have ages and we don't have comprehensive sampling from non-directed discards. For the recreational data, it only comes from 3A. And for the directed discards, we don't have at sea sampling of the discards in the directed commercial fishery. So we slice off the sublegal fish survey catch and say, well, it probably looks like this. What's that here? Again, those age compositions are in the data overview document. And we, yeah, go ahead.
We may have talked about this years ago, but have you compared that estimate of discards to like what happens in 2B?
Yeah, that's the one place we do have a comparison. And so they report the piece count of discards for every record. And so we have done that comparison, and I don't have the figure in front of me, but I present it most years to the 2B crowd because they are almost spot on. The average proportion or the percentage of fish by pieces that are discarded in the survey versus the fishery track over the time series almost exactly. It's
Now,
pretty impressive.
now they do because they're monitored and audited. But
Beginning
when
in
they were
2006.
not monitored and audited.
Yes,
They probably didn't.
they probably did. Yes.
So how far off could all the rest of the fishery?
They could be off. There is an observer program on both the West Coast and Alaska. It's not comprehensive the way it is in BC. There is some level of coverage in Alaska. I think it's in the 13 to 18% range. They can't land sublegal fish in Alaska. So there's kind of a hard cutoff on the age comps. We know, I mean, there can be a little bit of variability. They could be discarding a few fish that are close to that 32-inch minimum size limit, but slightly above. My sense from talking to people is that most people don't have the luxury in their business plan to even think it's a legal fish they're going to keep. So I think where the differences might arise is if there are some temporal and spatial differences within the calendar year where the fishing's occurring that would lead them to a slightly different demographic of sublegal fish. But honestly, I think it's probably a pretty small effect. Sublegal fish, just because of predominantly the use of 12 to 16 knot hooks, there's a pretty limited window of ages that are caught by longline gear. And so I think probably our survey's pretty good in terms of the age comps for the assessment and in terms of the proxy for the magnitude of discards. Your point is well taken that it's a good match in 2B, but we really don't know without comprehensive coverage on the prairies. So next. we do estimate for example, in the Western Gulf that the piece counts can be as high as 7 out of 10. So there's a lot of sublegal fish that are getting handled every year, and that discard mortality adds up. I think we estimated in the range of 1 to 1.5 million pounds in the last couple of years of discard mortality, which is, that's just the dead portion of discard. 16% discard mortality rate. It's quite a lot.
That's dead fish.
It's dead fish, not just handled fish. Just,
It's on a TCY of
just under 30. So it's an appreciable component. And as Alan can attest, we do a size limit analysis about every 3 years to see what the properties of that are. And the last couple have pretty much unequivocally shown that they could increase yield by getting rid of the size limit, because they would save that 1.5 million pounds. And actually, with the growth rates of fish right now, the maximum yield per recruit is actually pretty small fish, because the fish aren't growing very fast. But they don't want them, and that's why we still have a size limit. It's, I would say, basically purely an economic consideration. There's no biological rationale. And historically, there was a strong misconception that the minimum size was creating some sort of a spawning cage, that we would protect these fish until they matured.
just the males.
But 32
Protect all your
inches
males.
doesn't get you anywhere near maturity for females. And the males, and there are 25-year-old males that haven't reached the minimum size.
Yeah.
So there are some happy males out there that'll never graduate into the commercial fishery.
There's some little 95-year-olds this big down deep that don't do anything.
Just don't really get there. That's why the
Yeah.
processors, there's no good reason I'd be thrilled that they're seeing up there.
That's what we thought initially, is that there are plenty of flatfish that are marketed at sizes smaller than 32 inches, but there's really no appetite for it. And I will say, in the fisheries defense, they have had a bad experience with these big sablefish recruitments. A whole lot of small sablefish came in. They were forced to keep them in Alaska, and they've been paid almost nothing for them.
Yeah, I bought some at Costco in Boston, outside
Yeah.
of Boston. They were stinky and wormy. Gee.
So if we got rid of the minimum size limit, and there were one or more big recruitment events, there could be a case where fishery would have to keep those fish, and then there'd be a little value, and that could have market. So it's not a biological issue, but it is certainly a challenge for the fishery.
And to add to that, from the fish prices, when we sell undersized fish, the prices are not that much lower for small
Yeah.
fish. So the question is really not just on the processor side, that will be allowing that. And I think there are differences about how people can approach it on the processor side, because one processor, I believe it's exactly what you said. You just need to be willing to try different equipment that is used for other fish currently. But that will require a little bit of adjusting the market, adjusting the business plan and so on. So I think it's more about that. So people are still their way of doing things and the change that might.
If you got a big recruitment, you can show through the projections, like, we're gonna be doing this for a while. We might as well change now. That would be a good application for the projections, right?
Yeah, we tried to show that with the size limit analysis, that it's really dependent on where you're at, what your demographics look like.
It also, and this was something that actually you guys observed, one of the previous size limit analyses, is that it has disproportionate effects on different areas. So some areas would see very little change in their catch size distribution, and other areas, the areas that have 7 out of 10 sublegals would now all of a sudden be catching mostly sublegal fish. And so the value for an individual harvester in one area could be very different experience from somebody in another area. I think you all suggested that we ask for volunteers, see if any area wanted to try it out. And we got crickets.
0.
Nobody wanted to be the ones to try it. So since 1973, we've had the minimum size that's here to stay. So now that's a conceptual overview. There's a little more detail in the assessment document about some technical stuff. But that's a conceptual overview of how we set up and parameterize these models. I can hit a few more highlights when we look at the results, show you, for example, the natural mortality estimates and things. What I want to do now is orient you to the bridging changes from 2020. So I started with last year's final finished stock assessment model that fed into the annual meeting results. And I went through 6 different changes here. The first one is just extending the time series. So that actually doesn't change anything. I'll always do that first so that then this year, every bridging model has the same time series. And you can clearly see the effect of every change we've made since last year. So the first, extending the time series, the first year of the projection from last year's assessment is just put in whatever the commission selects as mortality limits is put in as the catch. And then at some point this year, we update the catch. And so we can actually show the sensitivity of it. Here's what you thought you were going to get. And here's what happened when we put in the actual mortality. And usually they're similar, although they're never the same. So that's a helpful step in the bridge. I won't have that part of the bridge into the phone. Then we updated the stock synthesis software. Happily, nothing to report there. None of the features that we use in this assessment were affected by any of the changes since the last version. I generally update the software on an annual basis, but I don't use versions that are not fairly extensively tested because we don't want to be the guinea pigs here on new features. So we wait till it's been tested. Try it out. Yes, years of experience on that. Not always so smooth in the past. Then we investigated updating to the new PDO series. I'll show you results on each of these things as we go along. Then I looked in depth at extending and estimating the male time varying selectivity offset. So this is when you may recall from 3 years ago, I extended all of the time varying selectivity vectors into the forecast period, but I didn't extend the fishery offset in scale into the forecast period. That was at a time we only had a few years of sex-specific data, and we had just started to model that in the previous assessment. And so we hadn't yet extended that into the full time series. So I actually did that this year, extended that out, re-estimated. We didn't have enough data really to estimate those signals on the degree of variability between male and female selectivity. So now we could retune that and extend it. Forecast. So I'll show you that result. Then we added the bootstrapped, the new maximum input sample sizes, and retuned the process and observation errors with that new cap on the sample sizes. And then finally, to really highlight it, we've added the maturity as the last step in the link. So we can show that. And I've also got a variety of sensitivities, so I'll show you several of those things, particularly the PDO and the maturity. So we can now step through some of these. So the first one, as I mentioned, sorry, just go back here. The first 2 of these, I'm not even going to show you any results, and I don't include them in the figures just to keep things simple because there's no difference in the results. The PDO, however, did have some difference. So this is a table showing you for each of the 2 long-term series models. On the left, this is the calculated relative increase in recruitment that we get with positive PDO regime. So 50 to 60% higher recruitment on average in a positive PDO than a lower, pretty substantial. On the right, it's the standard deviation of the recruitment deviations that are estimated. So this is after you've accounted for the stock recruit function and the PDO, how much residual variability is there in the recruitment deviations in log space. So the way to interpret that is the lower that gets, if we had the perfect recruitment index, that value would be 0. We would have explained all the variability in recruitment with the environment. What you see is that actually there's very little difference between each. So the top row is the previous index for the PDO and the bottom row is the current And the coefficients change a little bit. One of them goes down, the areas of fleets long coefficient goes down slightly, and the coastwide long goes up slightly. The the amount of variance explained is basically the same for the areas as fleets long model, and only slightly less for the coast. So despite the fact that the regime definitions change a little bit, and basically it's a wash. So my conclusion is the new updated PDO time series basically gives us the same information. So I don't see any reason not to update to the new one. I think I have, yeah, so here's the graphics of what the effect is on that time series. And you can see, actually, if you go back into the early part of the time series, early 1900s, there's almost no data in the model other than the people. So of course, those are changing things. But the closer you get to the end of the time series, you see the less effect there is on any of this. And I'm sorry, these are a little small on the screen, but in the document. None of these changes affect the overall trend very much, but they do have some small effects on the scale. This is actually the full bridge. So these are all the changes, all 6 of those changes together. The PDO on its own is just the black and the red lines, which I realize from your position you probably can't see. So, I guess I encourage you to look at the document to be able to see the difference. The differences for the PDO are primarily in the historical part of the time series. I think for some of the other graphics where there's more interesting stuff, I have some zoom in a little closer to be able to see. But for example, oh yeah, I guess I'm going to leave it there. Not much change. The next change, the next link in the bridging model was to retune and extend the sex ratio. So again, iteratively finding the new sigma and then extending that into the forecast time period. This is black to green, and you can see that those curves essentially fall on top of each other. They are different slightly, but in terms of the outputs, it was a trivial change. But what that means is that now we have all of the time varying processes fully extended into the forecast time period. So any little bit of extra variance is probably through to the decision table, to the 3-year projections. And then the next step in the bridge is the bootstrap sample sizes and then retuning the process errors associated with the random walk selectivity. So this is green to gold, and this was the biggest effect on the model. And this is because it changes not only the relative weighting among some of the data sets, but it also changes the relative weighting of the time series. And in particular, it makes the historical data less informative. So that the sample size, if you imagine one of the age comps, there's a reduction in the sample size that's larger in the historical age comps than in the recent comps because you've got more variability in the bootstrap now. So you're starting out at a lower level. The input sample sizes went down more for historical age comps than they did. So that's why you tend to see these differences tend to be accentuated earlier in the time series. Here, I've actually truncated the long models just to the more recent period. The whole model's still there. I've just tried to make it a little easier to see some of these changes and the effect. So again, this is green to gold. And generally, this had the effect of increasing the biomass in the historical period, but it was somewhat mixed at the end of the time series. And you can see for some of these models, like the areas fleet short model, the green and the gold are essentially on top of each other at the end of this time series. Similarly, for the coast-wide long model, the green and the gold fall essentially right on top of each other. So there were some sort of mixed effects across models with, like I said, the largest effect being on the historical time series. That step of updating the sample sizes. Keep clicking. And then this is the last step was updating the maturity schedule. And that's the gold to purple. And so that one, I mean, I think it's easiest to see up here because these two models are somewhat separated. So this is doing effectively what we expected it to do. Again, here, gold to purple. So it makes the spawning biomass time series estimates go up slightly across the whole time series because there's more younger fish. So through at all points in the time series, you get a little bit more spawning biomass. But the effect is slightly more pronounced as you get down into these dips here around 2010 and around the present. There's a little bit of a bigger gap between there because we've got more young fish in the population. So the difference is slightly larger in this time series. So this is not a huge effect overall. I mean, this is, you're seeing the entire bridge here. They all fit within each other's confidence intervals. But there is an effect of introducing this new maturity schedule. It suggests that the spawning biomass is slightly larger than we thought it was using the historical.
These are all absolute spawning biomass, but what does this look like relative to the reference? Is this even smaller there, but you see it scaling on the reference point as well, or does it not affect the reference?
Yeah, I have, it does affect the reference points. And I forget now exactly what I put in the document. The recruitment time series are also in the document. I just put spawning biomass here to see them. In terms of the relative stock status and the fishing intensity, I did look in particular at the first year of the projection with regard to, say, spawning potential ratio to see whether this increase in spawning biomass would correspond to like, oh, now we're fishing the stock at a very different rate. And I believe we were projected to be fishing in 2025 at an F52. And I think with the new maturity, it's an F50. So it's not a big effect on overall.
So even though we see impact here, that's sort of washed out.
I think it's a little bit muted it's definitely a higher, a slightly higher stock status. I think we went from 38% of B0 to 41 or 42% of B0 exchange. So there is an effect on the reference points. It's a reminder. So we had in this last year's process, we had a lot of people focusing on the amount of spawning biomass. Discussion about 150 million pounds versus 200 million pounds of spawning biomass, and you realize when we look at results like this, that a small change in our understanding of the biology, all of a sudden now have a different estimate of spawning biomass. Nothing changed in the water. It's just that we have better data on which of those fish are out there are mature.
Well, I mean, I think that so this is why I should be looking at status relative to reference. The absolute scale.
That's maybe a preamble to some of the discussion Alan's going to have about absolute spawning biomass. Okay, so that was the bridge. Then beginning from that, I'll talk through some model diagnostics, and then I'll go into sensitivities and other things. So we did the standard set of convergence criteria. These models are all in 80 model builder. They all had a reasonably small maximum gradient component. We did 100 rounds of jitter analysis where we start the model from an over dispersed set of starting points. And if you start them really wide, you can get these models to fail, but we're unable to find any better minima. So that suggests that at least we didn't have no evidence that we're stuck in a global minima. I will note that the areas as fleets models are technically just more challenging. They have a lot, because you have 4 fleets with time varying selectivity, they have a lot of parameters. They take longer to converge. They're more sensitive to starting points. They're just, technically, I would much rather have state space models than these kinds of approaches. They're clunky.
So it's still in ADMD?
Still in ADMD. There would be benefits to moving to TMB, but we'd have a custom model if we move to TMB. We are still, for better or worse, still thinking there's some benefit to being in a generic platform that's heavily tested and widely used.
Sure.
Fallon and I, well, off the Ballard Bridge tomorrow, there's a lot of analysts who would come in and take a stock synthesis model and have it running the next day. and our own custom model could be a while.
Well, depends how the custom model is set up, and
Yep.
we can set it up so that it's kind of, I mean, we've handed models to people and at the last minute, and they run assessments with them.
I would say that's been ubiquitous through the experience across fishery science in
Yeah.
the US.
Yeah, it just depends.
Right, yeah.
Depends
Absolutely.
on what that custom model is.
Okay, so no idea where those yellow things came from. It's interesting. He's doing all kinds of interesting things here. So this gives you a sense of the sample sizes that that result from the iterative approach. I put a couple of comparisons in here. The harmonic mean is one method that's used to tune sample sizes. The Francis weight is another method. And then I think it's also important to look at the magnitude of the residuals. I want to I think this is a good slide to mention that I spent a considerable amount of time this year working on one step ahead residuals. I think this is where everybody's going from Pearson residuals, but nobody really knows how to use them yet. So I worked with Cole Monahan extensively this year on learning how to use one step ahead residuals. We've put together a paper. It's actually in review with the Canadian Journal. I can share an advanced copy if you're interested. I didn't post it because it's in review still. But we felt like we needed to nail down some basic properties of those residuals and some good working guidelines of how to use them before we really went crazy applying them. Kind of feel not burned, but cognizant of my experience with model weighting, where we tried to get out in front of the literature. We felt this time we should just create the literature, and then I'll bring you models using one step ahead residual diagnostics after we have the method fully established. So that's the route we took there. But that was a considerable amount of time that was spent, and it really is part of this year's stock assessment development, even though you don't really see it in the document, because it is, I think, really what we need to be doing in all of these models, whether it's state space or other models. I think one step ahead residuals, everybody's going to be using them soon. So that's kind of an invisible part of this year's stock assessment. Again, that's in review, and I'm happy to share a offline copy with you. The takeaway from this is that I think all of these sample sizes, that the iterated input sample sizes are pretty reasonable. We don't get anything that's enormous. The ones that bother me the most are the region 2 and 3 survey sample sizes for the areas as feasible. You see, both of those have really low sample sizes. And those are cases where we have some systematic shifts within the age data that are highly model resistant. And I'll talk a little bit more about those. The figures are in the document. I picked out the worst residuals in any of the models and any of the data sets and put them in the document so you can see them. I'll talk a little bit more about what I think they mean and what they are when I get to the sensitivities. But those I think are the worst fitting places. And they fit the indices quite well. And those are the two data sets that I really think we should be fitting better. So I'll talk a little bit more about those when I get to the sensitivities. So here's now a look at a little bit of the results. So that each column is a model, and this is just some of the key leading parameters to give you a sense of how these things come out. At the top here is female natural mortality, noting that it's fixed in the coastwide short model. We get estimates that range from 0.22 down to 0.18 with confidence intervals that are actually reasonably tight in all three other models. The male natural mortality, we get an estimate of 0.16 for the coastwide short model. It's the only case where that estimate comes out higher than the females. And for all the other models, the male natural mortality is slightly lower. Similar, it really is fairly similar percentage lower than across all three models, even though the magnitude varies. So basically, you get the dynamics about right, and you need to see on the males needs to be a lot lower because there are not as many of them in the fishery, but the natural mortality component needs to be even just a little bit lower to explain
This is what I was asking about before. I mean, the confidence intervals in the other models, them are pretty tight, exclude the fixed point one.
Yep.
It makes me wonder whether there's a better fixed value.
It makes me wonder that too. I so far have not come up with a strong rationale that is independent of the other three models to change that value. That's we've been using, and you'll recall from 3 years ago, we had a lot of discussion about how to do this. The value of 0.15 came about fairly arbitrarily. It was actually a function of some of Bill Clark's work showing that, well, if you underestimate it by a little bit, you tend to be safer than if you overestimate it. They used, up until the late 90s, they used a value of 0.2 for these models. Of course, somebody did for all models.
This looks better.
Which actually looks pretty good given the range that we're getting here. My sense is 1.5 is probably a little bit low, but I have not come up with a good rationale, independent of looking at the results of the other models, to suggest an alternative value. And I haven't been able to find a way to estimate it in the Coast Wedge model independently.
How sensitive are
Highly, I'll show you that.
Yeah.
It's a direct scalar on spawning. So it is the most critical assumption in these models, which is why we argued to estimate it where we could, because then at least it's consistent with the data. So
Tried
that's,
using, sorry,
yeah, go ahead.
tried using a normal prior instead of a log normal?
No, because what would the basis for that be? You know, Owen's
It's
method,
less informative than a log normal.
you mean more informal.
It's less informative. The log normal has a peak and has a tail. It's asymmetry. So the asymmetry is an the normal doesn't have. So in this case, it's probably letting you, it's maybe letting you go out to the right.
Mhm.
Whereas a normal, it's, if it doesn't move off their prior, it doesn't move off your prior. You can't really tell what the data is.
The prior that we're using now is the meta-analytic prior that Owen Mel develops based on maximum.
You could
Better or worse. We could
use the
certainly.
point estimate and try a normal around it.
We could. We're, yeah, that's certainly something I can investigate. I think what we're gonna find is that the degree of constraint in the prior is gonna dictate.
Well, yeah, and it probably does it here too. Like the prior is influencing, well, I'm sure it's influencing those M's too, to some degree.
It is, although it's a pretty weak prior. I didn't repeat the figure. The figure's in the 2022 assessment if you want to see the actual distribution, but it's a pretty weak prior.
I see this one in figure 4.
It didn't. Oh, it is. Yeah, so it is in there.
It's not super. Oh, that's pretty informative. I mean, a normal, the idea behind a normal, it was in, I don't know if you ever saw it. This book, Nonlinear Parameter Estimation. It's an old one that Carl used to talk about and cite. He used it a lot. He didn't cite a lot of stuff when he wrote his books, but that was one of them. But he says specifically in there, the normal distribution is the least informative prior.
the nice thing about the one, since it's not zero.
That's, you've got too much data for that. It's unrealistic in that it might allow less than 0, but your data eliminate that possibility.
So this comes from longevity based. And there's
We use 55, which is the maximum age we've observed. We have a handful of fish, maybe 6 or 8 fish that are over 50 years old. And so, and actually two individuals at 55 suggesting that it's not just a one-off. It's a really old fish, and then they also have observed aging error associated with it. It's a fish stock, so it's conceivable that 10,000 ages from 1888 may have gotten something. But I think
Yeah, and then most of the others are based on upper.
just almost at all.
What about the?
My take on it is that people have more or less coalesced on longevity as the most defensible briar on M.
The then it all. Person showed.
Yeah, and Owen Hamel's work is, I think, just an update of or a parallel analysis to then work. Regardless, yeah, let's loop back to this because
Yeah.
I identify that value of 0.15 in the coast-wide short model as probably the most influential assumption made in this entire analysis,
Influential and weakly supported.
unfortunately. And that was our rationale for freeing that up in the Ares' fleet short model 3 years ago. And I had some expectation that we might be able to do better in this year's model for the coast-wide short, but by better, I mean something that's consistent with the data, not necessarily a higher or lower value, just finding something that's internally consistent with the data that doesn't require a fixed assumption.
And you tried constraints on that, very priors as opposed to fixing it.
Well, we could put a very informative prior on it and it would stay in the prior. But the data suggests it should be a higher value. But the fact that the data just want a very high value for M gives me, tells me there's something structural isn't quite right. And I don't want to just say, well, it couldn't be more than 0.28. So let's put a bound there and then let it go to 0.28. And that doesn't make any sense.
Yeah, you put another arbitrary choice here.
So, but I will show you, I've got a slide on how sensitive the results are to this.
That sort of makes, if we can't deal with this, it sort of makes me lean toward downweighting the coastline short model.
Perhaps,
Something's weird here.
yeah.
Let's not wait this one. I
Perhaps.
mean, I know you make me. One of them seems to have some flashing red lights. Well, no.
They all have their own flashing red lights. None of these models is perfect. They all have issues. So it's, yeah, let me get to my pros and cons of each model. I don't think I want to say much more here other than just to point out that we get pretty big offsets on the log Q when we make the transition from J hooks to circle hooks. And let's see. Yeah, I can see much else to point out here. Oh, just that the natural mortality scales the biomass estimates, and it also scales the recruitment, especially recruitment at age 0, because it's going to be subject to natural mortality. The magnitude, the absolute scale of the recruitments varies with M, even though the amount of fish when you get to the data doesn't differ that much.
I'm trying to interpret the survey log Qs there. Before you'd said that the CPUEs doubled overnight. Is that what this means? A log Q of 1?
I think basically, yeah. Sorry, I should have back transferred those.
Why is it survey log? Oh, no, that's your time variant.
That's the delta in 1980.
What about the survey? You didn't have a survey in 1980.
Well, we have pre and post data, so we estimate a delta. It's not only 1984. But remember, in that graphic, we have a gap where the transition from J hooks to circle.
But you had a partial survey going.
Yeah, we had some data before.
And they switched to circle hooks too.
Yes,
And the offsets.
exactly. That was why I included this originally.
Yeah.
I have the option here. We can switch over to the document. You'll notice I didn't try to put every figure in the document in the presentation. Yeah, you're welcome. And we can also go right into the output files. I suggest that maybe we go through the presentation and then we can go into specifics, maybe as needed to answer questions, or I can even call up some specifics if we can look at them tomorrow morning or whatever. It might be most efficient to move right into the rest of the presentation now. But I'll note that all of that stuff is available. So like I said, my philosophy in the document was I put all the fits to the survey indices in there, and I tried to put the worst looking residuals.
Appreciate it.
And then if you want to see better looking residuals, you can go into the model files and see, but that way, you can see this is as bad as it gets. Well, I mean, they are what they are. So
No regret, like the big.
right. So this, the next section is basically just trying to outline some of the pros and cons of these models. And I guess I would preface this section by saying all these models have their challenges and they all have their benefits. Each of these models has some things it does better than the others and each some things that it does worse. Again, the goal of each model was to create something that if we only had that model, we'd probably still be willing to do something with it. I don't want to put any junk in the ensemble, but they all are making different sets of assumptions. The coast-wide models, because we've aggregated the data into fairly small, smooth data sets, we tend to fit the data pretty well in the coast-wide models because there's not a lot of variability in it. The parameter estimates that we get out of them are very much focused on the recent time period because that's the only data in there. And we end up with pretty similar weighting on the fishery and survey age composition data, which actually kind of makes some sense, I think, based on the sampling properties. The weaknesses, number one, the fixed value of M has unclear basis, 0.15. We're not translating any of that uncertainty into the decision table. And as you'll see, there's a huge amount of uncertainty associated even with those pretty tight confidence intervals in the other models. We're ignoring all the historical data, and we're losing all of the region specific information due to aggregation. So are we really getting some of the resolution, and are we able to pick up some of these trends? I don't know. I mean, this is the whole argument of coast-wide versus fleet models. So definitely some pros and cons. And I'm not going to go through and read every pro and con for each of these models, but they do differ a little bit. And as I pointed out on the composition data, the areas as fleet short model, the big shortcoming I see is that it doesn't fit the regions 2 and 3 age data. So they end up being downweighted because they're not fit very well. And that, that's not, I don't like that very much because we have a lot of data there and it seems like those data should be pretty good. And so not being able to fit them. As you'll see when we get to some of the sensitivity description, part of that is I think they might be too good. I think we're picking up some things there that we can't model with this approach. It's not an explicitly spatial approach. I guess I won't walk through every bullet on all of these, just to note that there's certainly a list of pros and cons for each of these. I will point out in its favor, the coast-wide short model, I didn't include it here, actually has the best retrospective pattern. It's got the least retrospective trend of any of these in terms of an internal model retrospective. So that's one additional benefit that I didn't mention there. So I've highlighted their fits to region 2 and region 3. The coast-wide long model, when we get to the long models, we're buying more context. I would say it's really important for people to have some understanding of the historical period. So if we had no models that went back prior to 1992, it would be very difficult to put into context the productivity in the 90s and 2000s versus what we saw for the previous 100 years. So there's some value to having these models.
Yeah, otherwise, the recent period looks anomalously low. If
It does.
Exactly.
Exactly. And that period in the early 2000s looks like it might be a logical baseline when we realize with 70 years of age data leading up to that, we'd never seen anything like that in 70 years. That 87 year class and the year classes around it extended farther out into the age comps than we'd ever seen in the past. Yeah. And then the areas as fleets long model has some of the same shortcomings as the areas as fleets short model. It's also, this has got the highest technical overhead, takes the longest to tune. This is the one that I would really love to get into a state space framework. I think it would be a huge step forward. So I think with that, I'll move into uncertainty. We can certainly look back to any of these topics after I get through a little bit of the presentation. I realize I'm a little bit slower than I planned, but we still have some time. So I wanted to give you just some context on what have we looked at in the last decade. So these are all the different sensitivity analyses that we've published in the assessment document. So we've looked at the recurring themes here early on, and I list the ensemble because the uncertainty among models is a key point of sensitivity, comparing across the 4 models. Early on, you see a lot of focus on male versus female selectivity. We did a lot of sensitivity to that, and that's in the years before we had the sampling of the commercial fishery. That disappears in 2019 because we turned that from a sensitivity into something that we could deal with in the models based on Joseph's research program. So I think that's a great example of, we identified a major uncertainty. We created a data collection program to address it. We analyzed the data, put it in a model, and now it no longer shows up as a major source of uncertainty. It's something that we're monitoring and dealing with. Similarly with maturity, you can see maturity pop up, not every year, but virtually every year. And again, this year, and hopefully at some point we can stop doing sensitivity to maturity and just have better information. We had a lot of focus on unobserved mortality early on, and that's continued to pop up several times over the time series. And I'll talk to you a little bit more about whale depredation here in a few minutes. Again, this is just sort of trying to give you the bigger picture of things that we've thought about, things that we've been concerned about. And this also should give you some indication of how we develop the research priorities going forward. It's things that are of high uncertainty in the stock assessment. So the biggest uncertainty is the historical dynamics. So this is just the results of the coastwide long and the areas as fleets long model paired together. Sorry about that vertical line. I have no idea why we have that.
They're all more.
I know it's coming out of the projector. It's not on the screen.
It's a different.
I was gonna ask Colin, like, what's
Sorry
that
about
gray
that.
line?
Can't make that go away.
Reading.
I see the comparison of these 2 models as one of the bigger sensitivities. Unfortunately, this is not one that is easily resolved, and it has to do with the historical connectivity of the west side and the east side of the stock. So recall, the coastwide long model assumes asymptotic selectivity. The areas as fleets long model assumes dome-shaped selectivity on the east side of the stock. What that means is that in that historical period, when most of the fishing was in region 2 and 3, in the coastwide model, the entire stock gets fished down. That's the blue line. So we early in the 1900s, we fished the whole stock down. The black line is, so now the old fish are relatively unavailable to the east side of the stock. So we don't have as big an effect on the biomass of old fish until later in the time series, after we've been fishing much longer. So we draw that west side of the stock down much more slowly. And that's what leads to this big offset that leads all the way up into the 2000s of, well, maybe there was more biomass. Well, that essentially is equivalent to more biomass in the west side of the stock implicitly in that model. It's basically saying those old fish in the west side of the stock were less available than just instantaneous mixing. So probably the reality is somewhere in between these 2 assumptions. But I think this is, we often get asked, well, how can you not know how much biomass there was? Well, because the data was only from pretty much from the east side of the stock until the 70s or 80s. So we really don't know. So we're capturing that. The nice thing about these is that you see how closely they come together at the end of the time series. That's because they're fitting to all the same data in the most recent time period, and we're getting much they have to match the fishery and the survey trends at the end of the time series and the age comps. I don't think there's any way to resolve that historical uncertainty. But what it means is that when we think about like, well, what's the 100-year average biomass level? Well, we really don't know. We know where we are now pretty well, but we really don't know what kind of biomass could have been out there historically. And I do think it's important to express that uncertainty. So that's a big a sensitivity analysis, just comparing those two ones. And that is captured, propagated through our ensemble. So here's the PDO. So this is with and without the PDO. The blue is the new PDO series and all the bells and whistles and everything else updated. And the black is without any PDO relationship at all. And it's interesting, there's not really that much difference in the biomass time series. In the document, there's also the recruitment time series, if you want to see that. If anything, the coastwide long model is slightly higher at the end of the time series without the PDO, because it doesn't have that signal saying, well, you're in a low PDO. The recruitment, which is pretty well informed, but not perfectly well informed toward the end of the time series, is definitely being drawn downward somewhat by including the PDO relationship. So that's with and without the PDO. You already saw the old PDO to the new PDO. We looked at steepness, and I don't know why I only have two models here. Maybe I just shouldn't. Okay. Well, all four models are in the document. I think I just picked out two here because the other models are virtually unchanged. You see the coastwide short model, the change in steepness, we're estimating the recruitment's almost free. It's pretty much independent of the stock recruit relationship. Interestingly, in the coastwide long model has a slightly larger effective steepness, and the lower the steepness value, the higher the biomass estimate. I'm not sure if that's intuitive or not, but that's the way it turns out. So if we were to force the model to have a lower steepness,
It's not correct.
we would have
It's
to.
bigger.
I think that's the conclusion. Yes. Then we did sensitivity to natural mortality. So that's what we were just talking about. The base M is in black. That's 0.15, and it's 0.12 and 0.18 in red and blue. So if we were to move M up to be more like the other models, you can see it's basically a linear scalar on the biomass system. And so this is definitely sensitive to the fixed value of natural mortality.
This makes me want to talk more about this than the other stuff. This is
And
where it really matters.
you'll recall from 3 years ago, we spent most of this meeting talking about natural mortality, and we made some progress on the areas of fleet short model, but we didn't gain much here. We talked about, well, maybe we should just try to include this in the ensemble. So instead of having 4 models, I could have 7 models, and I could take the weight of this model and spread it out over these 3 versions, these 3 levels of natural mortality. Well, should it be 3 or 5? Should I use 0.12 and 0.18, or should I use 0.14? It starts to become a whole lot of arbitrary choices. Technically, it's a lot more model running when I need to set up models when I'm going to do it. But there's some, there's a case to be made there that there's some uncertainty here we're not propagating. So I'll throw that out there as a point to consider this week.
This is a pretty small range of things that work here.
Well,
The other ones were up at 0.2, right? So
Yeah, so that thing
Yeah.
would be even.
yeah, I tried to bracket the value we're using, but yeah. I mean, I would say a value of a range of 0.06 is terribly small for him, but it's,
well, I think it's more that the range that goes down. It doesn't go
Yeah.
as high as the others.
and again, this isn't a proposal, this is just a sensitivity to make sure it's really transparent how sensitive it is.
No, this is really helpful. It's really sensitive, and it also, unlike the other sources of error, the sensitivity doesn't go away.
Right.
This is sensitive all through.
And it's almost just a scalar. It doesn't really change our trend.
Yeah,
And it's not going to change the relative scale in terms of reference points because it's just globally scaling. It's more a scalar on absolute biomass.
it doesn't change. Wait, so let's just change the status relative to reference.
No, because it's scaling the whole works.
Scaling the reference points.
Just like you're seeing here, it scales high biomass and low biomass. Okay. So this is the sensitivity to maturity. And recall, we had three different cases. We had the historical maturity, which is blue. We had the updated maturity, which is black. And then here on top of the black is the non-truncated maturity. So I'll confess, this is another reminder to me about making predictions about complicated models. I thought to myself, a little bit of maturity times a lot of fish is probably going to matter. And I was really worried about this. Colin can attest. I was like, I don't know about these. I don't know about that little tail. It makes me nervous. It turns out it doesn't turn into anything. It's not enough maturity or enough fish to really scale the problem. But I actually kind of thought it might. So we did the sensitivity anyway, just to make sure. I still think it's better to truncate because we've never seen a fish less than age 7. But if we find one, I don't think we have to worry about it rocking our whole world of understanding about how it's not.
It's more about biological relevancy.
Yeah, exactly. So the red falls on basically on top of the black, meaning that if we don't truncate, we get truncated. That was reassuring to me, not surprising.
Sorry, I'm still about M.
Yeah.
What is that? So that we saw what it means for the spawning stock biomass. You say it cancels out when you look at the biomass relative to the reference point. What does it mean for the TCY?
This model is often the lowest model in the set. And so it could have some implications for the TCU. As we saw in 2022, when we moved the coastwide, the areas as fleet model, we estimated M, it went to a higher M. Where collectively, the distribution from the ensemble shifted up. We ended up with a perception of the stock being larger and more productive than it was before. I think this would be potentially a smaller effect because it's only 1 out of 4 models, but it will have an effect. If this model looks more productive, it will change, especially the lower tail in the decision table. The probabilities of low biomass will be less because this will get direct scaling. So it's not without implication for the process. I mean, my sense is that a value of 0.15 is conservative for this stock. The evidence to the contrary, and we did lay a lot of this out in the 2022 assessment, the one data set that would suggest perhaps a lower natural mortality rate was the tagging study in the early 2000s. There were some estimates of natural mortality there that were closer. And so we actually explored using a prior at one point based on those data, which would still be inclusive of values at this range, but would be centered at a much lower value. That seems too low for a fish like this. That's, that's the data that we have. Of course, whenever you try to estimate M from tagging studies, it's the assumptions about all the other components in the study that become important.
Right, which is why you usually end up with this there was high from tagging studies.
Well, we had some interesting challenges in that pit tagging study. For example, we thought it was going to replace the assessment. We thought it was going to be a method to monitor the stock. We put the tags out, we'd get them back, we'd get an estimate of the stock size. We got an infinite estimate of stock size in 4B because we didn't get any tags back. So that, it didn't quite work. And in other areas, we also got some counterintuitive. So that didn't replace the stock assessment as much as everybody wanted it to at the time. Yeah, I don't know what to say other than the first presentation I ever heard Bill Clark make was basically, we did this awesome study. We did all the things you should do, like double tagging and blind tagging, and they tagged tens of thousands of fish, and they had wands and tag recovery in every port up and down the coast, and they just couldn't make sense. So it just didn't quite.
Same exact thing happened with Black Sea Bass. Massive tagging study. some people involved in the estimate there of how this stuff realistically not. You never see a 4-year-old fish.
Yeah. I don't know. Tag, everybody loves to tag fish and
Yeah.
it never tells you what you want it to.
And in theory. So,
In theory.
So we looked at maturity. Oh, yeah, sorry, I gave you both. So this is the short models maturity and this is the long models. Again, you can see that the change to the new vector isn't huge, but it's positive over the whole time series. The blue to red is the, or the blue to black and red is the change from the old maturity vector to the new maturity vector. And then red and black are essentially on top of each other. You can see. So I've already mentioned the lack of fit to the region 2H data, particularly in the areas of Fleet's short model. I went down a long rabbit hole trying to understand this. So I could call up the figure for you maybe later or tomorrow if you want to see it, but the residuals basically show a temporal pattern. There's a lot of younger residuals in the early part of the time series and older residuals in the later part of the time series. It suggests some sort of a temporal change. And I couldn't figure out why, with time varying selectivity, why doesn't selectivity just soak that up? Like it seems like time varying selectivity should just soak up a time varying signal. So I took half the data out. I took the last half out and I fit it and it fit well. I got an estimate. And then I took the first half out and it fit well and I got an estimate. And I took the two parameter values and I made sure that I could get between the two. And then I put them back in the model and I still couldn't fit it. And so the conclusion is that it's not the shape of selectivity, it's the relative catchability over the time series. So I couldn't, without allowing time varying catchability, couldn't do it.
it's odd because catchability times selectivity.
But it's the asymptote. So it's the peak. Well, in this case, it's don't, but it's the peak. It's the fish at the peak. So what it's suggesting is that those fish that are basically fully selected may have had a shift in their overall availability compared to the coastwide stock. The obvious thing to do here is to introduce some time varying catchability. Problem is, if you do that on your survey, what have you got? You've got no index that's not time varying. So that was a full stop. And my conclusion is that without actually modeling spatial dynamics, where these fish, what we're seeing is a shift from west to east of the stock. We've seen it in the data. We've seen the biomass. Historically, we had more biomass in the west and less in the east. Now we have more biomass in the east and less in the west. And in a model that's using areas as fleets, we can't capture. So I think some of that lack of fit is spatial dynamics that we just can't proximate within areas. So that was a long dead end for this model that I think could be addressed with a truly spatial model, but short of allowing time catchability, I think it's kind of a dead end for these kinds of models. But I still don't like having those data down-weighted heavily. But it is what it is. The second part here, there's quite a long description. I tried to boil these down into pretty straightforward descriptions here. There's a longer narrative in the document, and I'm close to done here. But we've had a lot of questions in recent years about whale depredation. We see in the document, you'll see in the recruitment time series, we had sort of one level of recruitment until about 2005, and then we've had much lower recruitment since then. One conclusion is that we've had a change in the environment that's led to, on average, lower recruitment. It's consistent more or less with the PDO signal we're getting. We've been asked a number of times, well, could this be due to whale depredation? Could it be that now we've got this unobserved source of mortality that's operating on the stock, and that the lost productivity in this recent period has actually increased whale depredation? So I try to run where I said, okay, starting in about 2010, which would correspond to when those recruitments sort of enter into the biomass, what if we started increasing, what if we increased the level of whale depredation? So assuming that the whales are just eating whatever the fishery's catching, that's just more catch, right? It's unobserved catch. So we put one catch in, but the true catch is. Problem is, you do that and it doesn't change the recruitment signal, because the offset in recruitment is being created by the age data, which is telling you something changed in the recruitment. So even at really high levels of whale depredation, what it does is just scale the stock, the biomass, but it still has that. So it doesn't really help us in terms of modeling, but I think it's important sensitivity to be able to tell people, look, there may be unobserved whale depredation, but it's not what's creating the apparent signal. That it's not a good explanation that set to a lower productivity. That was another, and I don't need figures of that because it.
Blame something. It's always the whales or the seals.
Yeah. Well, we can attest, there's some whale depredation going on.
Sure.
But it doesn't appear to be easily explainable as a source for the low productivity we've seen in the last close to 20 years now. Okay, these are the retrospective analyses. I apologize for the colors. When you get out to 9 different colors, it becomes hard to come up with new colors that show well. These are the 2 short models. As I mentioned, the coastwide short model has probably the least amount of retrospective, although it is a slight positive retrospective, meaning the biomass estimates go up slightly as you add more data. The areas of fleet short model has the opposite. They tend to go down slightly, although most of them stay inside the confidence intervals of previous models. The worst patterns are in the long time series models. And these are interesting because the coastwide long model seems to be more in terms of trend. Historically, not much changes, but the trend changes a little bit here at the end. And the areas as fleets long model, the trend is mostly the same, but the scale changes. So we add more data and the scale comes down. So both of these have some patterning there.
These are terrible retrospectives.
They're not terrible. They're nothing like they're nothing like the retrospective we had back in the early 2000s.
That is a difference of about 80 million pounds in whatever year that is.
Yeah.
Your longest peel is almost double the size of the recent one.
Now notice, but do recall that 8 years ago, there's only 1 year of sex ratio data available. So we were not using these models back then with time varying sex ratios with only a single year of data to anchor the whole time series of sex ratio in there. So we would expect some behavior as we get back, especially to these older models here, the 6, 7, and 8 year old eels.
But
yeah,
estimates of R0 is R0 for each of these. I would imagine it's R0 is changing.
it is R0 that's changing. In fact, I think my next slide is showing you that it's not M. So the first thing I wanted to make sure is whether M was changing, because if M is trending, then it suggests something. But these are the 3 models that have estimated M. This is female M in those 3 models, and this is the value for all of those peels. You can see there's no clear pattern. So it's R0 that's changing. You will note that in reality, the models that we've been using have not shown that kind of a retrospective pattern. So these red dots are the terminal estimate of each of the actual stock assessments each year. We have seen a bit of a retrospective pattern in the last 3 assessments, and that's the last 2 years. Much of our exploration has been in why are we seeing this drop in the results compared to the previous years, and it's been driven almost entirely by the fishery data. So last year, for example, and you can look at last year's assessment document, I sequentially added each of the data sets, updated the cache, all those things. And you'd get, if you did that, you'd get something that went right through this point right here until you added the fishery data. And the fishery data is what pulled it down. It was just, and this was the same thing the year before, although not quite as pronounced. Both of these years, it's been the fishery data. So this gets to your question, Olaf, about whether or not we're seeing a signal in the fishery that we're not picking up in the survey, or whether the fishery is picking up a signal that's not related to the population. And I would say at this point, we can't tell the difference between those. But what I would say is that what we're getting in the results is something that is responsive to the fishery. Because we have uncertainty in the survey in recent years, it's the CVs are not as tight as they used to be. The fishery signal's coming through more strongly than it has in the past. So for better or worse, we're responding to this signal without really knowing what it's being caused by.
Well, once you finally do get it.
I hope so. If and when get a better survey, yeah. But this has been, for the last 2 years, this has been the major point of uncertainty. Why is this fishery, I don't have a good comparison here, but in the document, you'll see the fishery, the weight per unit effort in the fishery dropped the last couple of years. And in the survey, the numbers that we fit in the assessment model have been basically flat. They actually went up slightly last year. And so we're getting a slightly different picture of what's going on in the survey. That's been a major point.
You're really worried about the bias issue that we've been talking about a lot. Survey.
Yes, us too.
Bias.
Exactly. I realize it's 3:30. Nothing's changed in the ensemble methods. We use the maximum likelihood approximations for a posterior, and we equally weight the models. So we basically resample from the distribution of management quantities and weight them based on the estimates that we get. So we're basically sampling from these PDFs, combining them. This is that drop in recruitment that I was talking about. So we had apparently one level of recruitment until 2005, and then we've had a lower level since. That's a pretty good illustration of that. And these are standardized. So each of these is based on the average within that model over this time series, just so that they're all on the same scale, because natural mortality differs, just to show you that we're basically getting the same year class estimates from all four, even though we've got different natural mortality rates. So
That's relative. Scaling's different.
correct. That's all relative to the mean. So that's why they're all, the value of one is right through the center. Just to be able to compare the relative. So I did want to tie back a couple of larger uncertainties. The first is that when we had first embarked on the study that Andy was telling you about, we had some concern that biological region 4B might be a separate stock. And you'll recall that we actually wrote some narratives saying, what would we do if it was? Well, we'd separate it off and assess it separately. I think we've decided that's probably not a good idea. It's the same stock. It doesn't mean it's not demographically somewhat isolated, but it's not a separate genetic. There isn't some unique piece of gene that we need to maintain. As I mentioned early in the presentation, we do have some concern over linkage to Russian waters, the effect of Russian catch on our part of the stock and vice versa, but I don't have a clear suggestion of how to address that. We did not this year and have not for a couple of years done a lot of work on extending these to Bayesian models. I do think that state-space models is probably a more fruitful thing to focus on than Bayesian models at the moment, even though I do have a soft spot for Bayesian models in my heart.
Yeah, I mean, all of the arguments you made about, falling off the bridge, moving to land.
Yeah.
Increasingly, there will be people who know how to use WAM.
And it's actually, there's an equivalent that's being rolled out in Alaska as well. There's basically Cole Monahan has rewritten WAM for some of his stocks, but they may actually just be using WAM for other assessments as well. So I think you're going to see similar models moving up around, whether it's exactly that platform or not.
And Sam, I guess.
And Sam, although again, Sam doesn't have much in the way of richness. It's very ICs focused. It's simple data sets. They don't even admit there is aging error.
That's all you had to say. IC, typical IC stock assessment.
And then whale depredation. So the uncertainty in mortality. I mean, all these models are conditioned on us knowing them. So any uncertainties there is none. So discard mortality rates. 10 years ago, it was all about uncertainty and discard mortality rates. We spent tons of time on that. It's not so high on everybody's list. Everybody wants to blame whales now instead of trawlers or both. But these are sources of uncertainty that I can see ways to include that in the ensemble, but it's going to be, I'm not sure it's going to be transparent and simple enough technically to really be worth squeeze. And that gets us pretty much to the end. The research priorities, we've updated to take out some of the things that were priorities that we've addressed. We're going to obviously be elevating the highest priorities to the 5-year plan, which will be coming up soon. The next 5-year period is coming up. And I like to keep this longer list in the document just to maintain a record of all these things. So in the document, you'll see the longer list of research priorities. But for the 3 categories that we use, these are the top priorities that I see coming from the stock assessment. I'm certainly open to other ideas. But I think the fecundity relationship and evaluation of whether skip spawning is an issue is top of the list biologically. And then understanding what's affecting size at age is next. If we could better understand size at age, understand whether and how much of an effect of fishing there could be on size at age, what other factors might be affecting it, and how to, especially for Alan, how to project size at age forward in the future. That's huge. In terms of data, we certainly need to continue to collect sex ratio information from the commercial landings. This is a key scaling variable. As I said, it affected our understanding of natural mortality because the model is estimating Z, and then we partition that based on how we think catch comes out. So this is critically important, and we only have this data set starting in 2017. So the more we develop this, the more information content we have in these models to anchor in all these other processes. The sex ratio is really the linchpin for the scaling of these models. I do think that maybe I'm swayed by current sentiment, but I think that understanding and dealing with marine mammal depredation is a pretty important component. And I'll say for the record that I wrote this before Claude and I and Joseph went out on the study, but watching a set with 21 sets of halibut lips come back reminds me that, yes, this is really an important issue for the fishery right now, if not for our understanding of stock dynamics.
In a small subset of
In a fairly broad subset, we're seeing some whale depredation across most of the zone.
oh yeah.
The west coast down here doesn't see much, but they have some in British Columbia. In some new reports of killer whales in British Columbia, which is fairly new behavior. Sperm whales generally are on the deep edge from 2B up into the Central Gulf and not really anywhere else. And then increasingly in the Western Gulf and the Bering Sea, it's an issue. In terms of technical development, the highest priority is this interplay back and forth, making sure that we are doing things in the assessment and the MSE that cross over well. But the second highest priority, I think, is developing some state-based plans for how. That's a good place to put our effort in the next couple of years. And then the third is this issue of what to do about natural mortality. I don't know what to do right now, but I think it's a high priority to figure out something other than arbitrarily setting it up.
High priority, low prospects for solving.
Perhaps.
If you go to the state space approach, would you do all 4 of them? Would you continue the full model ensemble, or do you have one that you want to tackle first?
I think we would. Well, I'm open to ideas. My idea would be to build a fairly simple state-based model. Maybe it looks more like the coast-wide short model to start with, just to get something going, and then see how it goes from there. The nice thing about using an ensemble is that we could choose to add a state-based model to keep the 4 we have. We could choose to replace one. We need to think carefully about weighting and make sure we weren't sort of double dipping on different things. But that's a thought experiment that could be had. If it's a coast-wide short model, we could split the weight. Who knows? But But I think getting one up and running and evaluating it and sort of seeing what it takes to fit the data sets that we have would be the first priority.
Where would the true random effects states-based model be most beneficial?
Recruitment selectivity.
So that suggests maybe not coastline shore.
Well, or maybe. I mean, we still have time varying selectivity there. It's just asymptotic. I think it could be a useful approach. I mean, I could imagine a case where we replace all 4 of them with a state-based. Because really what we're trying to do, this is a clunky way to do state-based, right? We're iteratively tuning signals, which is really just not quite a very elegant way to do random effects models. So I could imagine a case where we might be able to replace all 4. I don't know that we could go there in one step, but I think there's a lot of prospect for improvement there. So it's certainly where I would propose we put the technical development effort the next.
I would suggest, I have a draft recommendation that the states-based model be developed for the next full assessment cycle.
3 years? 3 years to do it? Sure. Sounds great. Ask me in 2 years and I might have cold feet, but no, it seems like, I mean, like, as we've discussed in the past, we've been trying to wait until some of the platforms that are out there are getting closer to having the features that we need. Because we haven't wanted to go into a full custom model mode for all the reasons we discussed.
But you said you feel like you would have handled
I think it's getting close. I haven't obviously built a model, but from talking to Tim Miller and Cole about it, I think that the capability is getting close. I know there are a couple people in Alaska that want to apply it to flatfish assessments there. And again, they're going to need dimorphic growth. So we won't be the only ones investigating how to make that work. So I think there's some avenue for development there. Seems like after talking to Anders about SAM, I don't think they have any interest in adding that kind of capability to SAM, nor aging error, nor any things we need to have. So that doesn't appear to be a fruitful
I was on a review panel with Sven a couple of years ago now, last year. And he made a comment about states-based results. Saying that the random effects can soak up a lot of model specification as well, and it sort of works and works. Something like that. I don't know how valid that is, but
I have some concerns about that approach as well. I mean, especially when I see state-based models that have random effects on the numbers at age. So we generally like some biological rules, like fish can't spontaneously generate between ages 8 and 9. And a lot of those models have random effects, which effectively do that. Fish can appear at age 9 that weren't there at age 8. And you don't see it because there's catch and mortality. So the numbers at age 9 aren't larger than the cohort at age 8, but there were fish created in that intermediate step. So there are some things there that,
Well, the more complex the models get, the more sophisticated your analysis. As long as you can parse out the components of a model, what's the production, what's the recruitment, what's the mortality, right? As long as you can see all that. But normally, like, you probably don't do that here. Something you spit out with deviations and stuff, but not, for example, the production. Right? You calculate the production from year to year, where it's going. Yeah, and what age classes are actually doing cohort specific. You know, Bill used to do that. I don't know if we still have all that stuff, but he used to do the cohort models, right? The catch curves by cohort.
you know,
Maybe
do
just
that.
to show that, but anyway,
It's,
the nice thing about the state-based models is if you don't have all that, if you don't have enough true random effects in processes that are like that, it pushes you towards models that are not right. Like it forces you like here, for example, you get M misspecified. Well, the only thing it can do is move the model to some, right? Change B0. That's the only thing it can do, right? Versus saying, yeah, it was, something happened. That would move instead. So that's the trade-off, right? You've got to have that. I can't see. I mean, we used to, back when I was a grad student, it was like stationary. It's like real life, you can't use them. They're almost unusable. They're so different. But, yeah. The estimates they give you a lot of them. So that's really, in terms of if it takes you 3 years to develop, you could build a state space model in a couple of weeks. It's all this other stuff.
Yeah. And we
Because I priced this stuff out, like, for contracts, and it's like, this is what it's gonna cost, right? And then you find out, oh, it took us twice as long to do these things, and analysis of the model takes a lot more time than you think.
And our data sets are non-trivially rich in terms of,
Yeah.
just all the little things like J-hooks to circle, this, that, and, there's a lot of things to deal with there.
Yeah, it's the downside of all this stuff.
It is. Yeah, we're well past the sweet spot of having enough data to fit a model, but not too much to make it hard. For sure. But nonetheless, I think that's where everybody's going. Everybody's moving towards space models. And so I think we need to keep up and working in that direction. But I don't know exactly how they would integrate in, but with an ensemble, I think we'll have an easier path to integrating them in cases where they may have been using the same nose plan and making an abrupt shift into a state-based.
Yeah, that's right. You're at least to making a bus.
I'm basically done. So from here, just to refresh you on the process, we'll have the summer between now and SRB027, we can provide responses, additional analyses, anything you need to do. We can take back anything we've rolled out here if you don't like it. After SRB027, then just the rest of the data go in and that's it. So whatever we need to have your request, ideally your request at this meeting will give us enough options in September that we can all be happy with a choice to move forward with no further changes after September SRB. I will have possibly time for the SRB, but not guaranteed. We will have the 2024 commercial fishery sex ratios analyzed, and then subsequent to the SRB meeting, I'll have all the rest of the information, the mortality and surveillance, sort of stuff, but probably not in time for the SRB, and definitely not in terms of a 30-day deadline before the meeting to have it written up. So just so you're aware. So the requests for this meeting are to note the paper, note any changes that you'd like to see or additional analyses for the fall. And then if you can, be clear about which things are longer term analyses, things that could occur for next spring or beyond. If there's a request for the next full assessment or a request for next June, nice to separate those from things that will be delivered in September.
So getting back to that retrospective thing.
Go back there. Sure, I don't think
Basically, the product that you're providing is the decision table.
Yeah, off the stage.
And it's showing various small probabilities of crossing certain thresholds. It would be helpful to see the implications of the retrospective for those. Is it because the probabilities are so small, they can be sensitive to retrospective? So, for example, let's see why you couldn't do it, but for each one of those retrospectives, make a decision table, or at least pick out some metric off the decision table. The whole thing. One that people tend to focus on, or whatever. But what's the probability of something happening? Just see how that varies across peels.
Could do that. I'll note that we're not using the peels. Peels don't correspond to the advice that was given. What I was showing you, there's a within model retrospective. So the actual ensemble result has not evolved in the way that it would look if nothing had changed in these models except.
Right, as I was talking, I was
Yeah.
I was picturing the last one you showed,
Right.
which is the ensemble retrospective, which was fairly minor.
So I can show you, what I could do pretty straightforwardly is put together a summary of how the actual decision tables have changed in the last few years. And I could track a few metrics through those so you could see how those probabilities have changed. And that would be exactly what people have been making decisions on. So you could start to get a sense of variability in the information people had. I mean, I could do the other as well.
That's based on what the assessment actually said.
Right,
That's a between model.
right. Which I think would be less confusing to people than a within analysis. Not that the retrospectives are also important, but they are not how things actually unfold.
Yeah, but even for the ensemble retrospective to see what some decision metric would have been. Instead of just biomass retrospective, it's basically something relevant quantity.
Yeah, it's kind of put up and ask no. It's like, this is what happens to
And
the spawning that biomass. That's not actually what decisions are being based on. Sometimes that gets canceled out.
Well, a lot of it is. I mean, the trend in the spawning biomass is one of the key things that they. What's the probability of a decline in spawning biomass 1 or 3 years? But I can certainly pull those metrics and you can see how that has evolved over time.
Would that be looking at one specific year in the past, creating the decision table on, say, 2020? Because, I'm trying to think of what is the retrospective metric, what's it comparing to? Because if you take 5 years off of data, you don't want to be predicting that in 2025.
Oh, so you'd have, for example, a time series of the length of the retrospect, so it's an 8-year.
Yeah.
Longest peel is 8 years. So you'd start, okay, 8 years ago, the probability of a decline, whatever, was 0.03.
Yeah.
And then when we did the assessment the next year, let's see, so when you did it the next year.
Yeah.
Uh,
You actually have data. We tried to do this with Hake and we run into, it's not as easy as you think. What we thought with Hake's like, oh yeah, well this would be, and then you start thinking about it, it's like, what does it mean? Once you have data, when you're trying to look at something you tried to predict earlier.
well, you'd take, so the next year you'd add the new data. Take that model and go back and rerun the projection, starting the projection from the previous year.
From all the parameters that you've now
Yeah.
listed.
Yeah,
Yeah, that's a way to do it.
it might take a while.
Yeah.
The other thing which I did do once for albacore tuna was to make a forecast. It's kind of what I'm describing. It's kind of a predictive, because you're forecasting. I'd have to go back and see exactly. It's been a long time since I did it, but that's kind of the idea. Is it's looking for how good are your forecasts? I was looking at the coverage. Yeah, that's what it was. Go back and look at how your original interval, how much did it cover the actual?
Right.
When you actually got there and looked at the uncertainty in the biomass at that time.
So I did look back at the point I was asked the question, similar, perhaps the inverse of this question was, how is the decision table doing? So what they wanted to know was, okay, you said there was a 41% chance the stock would decline, and then it declined. Does that mean it was a good estimate or not? And so I looked at it across a number of years, and we concluded that what actually happened was pretty plausible every year. You'd expect some of them, occasionally something implausible is going to happen, but most of the time, it's a 50-50 chance, it could have been either higher or lower. You could, if you had 100 years of that, you could create a distribution and it should be uniform, right, relative to your predictions. But we sort of concluded it didn't tell them much, because if there was a 40% chance it declined for 3 years in a row and the stock went down, is that bad? I mean, stock did go down 3 times in a row. I mean, you can calculate the probability of it's binomial. You know, what's the chance of
It's
getting?
hard to do on probabilities, but if you said, you're under this TCEY, the stock's going to decline by 6% over 3 years. You could look at that and see if the actual decline over those 3 years. You'd have to take into consideration what was done in the other couple of years, but you could see if it was 6%. So you could look at accuracy. So that's basically forecast accuracy.
It's not hard to do with the probabilities either. It's just a receiver operating characteristic or the area or if you have enough data.
And I guess that's where we had the challenge, is that we have 10 years, but the models have changed during that time period. And every 3 years, we have a new set of models. So, I mean, I'm not crazy. Don't get me wrong. I'm not crazy about those retrospective patterns, but I realize that we don't use these models for 8 years in a row. These models get updated every 3 years. So part of this is, you tune the sigmas to get something that's consistent with what you have right now. But if you change the sample sizes or your data collection changes, the issue on the fishery side, the smoking gun that we see on the fishery side is this issue that came up years ago, which is that we have incomplete CPUE data when we do the stock assessment. And the data at the end of the year tends to have lower catch rates than the rest of the year. And so what happens is we run the assessment and then we run the next year's assessment, and the previous year's CPUE is lower than it was at the time we did the assessment. That's really not a model retrospective issue. That's a data retrospective issue. And what we did 10 years ago now is to say, well, let's just increase the variance of the terminal year of CPUE data so that we don't fit it into the exclusion of other data, because we know it could change in that way. It doesn't every year, and it doesn't in all areas. So it's not like we get a straight bias correction that fixes it. But the problem then is that this has happened 2 years in a row where we've gone back. Not only do we get a CPUE that's lower than we would have expected, but the previous year is also lower than the value that was used in the previous assessment. And we've talked about, well, ideally you would just, if this is happening only for a fishery dependent index, you'd fit your survey instead. But then we have this issue we've got right now, which is that we have concerns about the survey coverage. So we haven't wanted to just throw out the CPUE. I mean, the quick solution would be don't use the CPUE until it's final. Right. But then we wouldn't be picking up the signal. So then we'd be a whole year lagged. So we've been kind of stuck.
There'd be more uncertainty.
We would have more uncertainty, but our point is to be convinced. Because the fishery data
It could be biased if you include it.
Exactly.
I mean,
And so that's where we've been
Yeah.
stuck, not knowing quite what to do the last couple of years. So we've gone ahead and included it, which means we've had this 2 years of, in the ensemble, a slight retrospective downward in the ensemble, but we don't know what's causing it. We do know that the CPV series has gone down, and it's gone down in the second year back as well, both years in a row. I actually have a series of slides I can show to you in the morning that I used to explain this situation to the commission last year. But up until the last 2 years, we weren't having that problem. We either didn't see a big offset in the second year back, or it was consistent with the survey and it wasn't creating any kind of an offset in model results because it was giving the same signal as the survey. So we really, There are different ways to fix it, but the fundamental uncertainty is we're getting a slightly different signal from the fishery and the survey. We don't know which one to trust. And because the survey variance has gone up in the last couple of years, the model has got more weight on the fishery.
But how much? I mean, we haven't seen like massive increases, at least in the things that we're presented with.
No, it's not a huge effect, but it's a trade-off between the two, right? So just a little bit, if the fishery's pulling it one way, that's the trade-off that's occurring. Variance of the coastwide index, the log standard error. It's gone up from 0.40 in 2021 to 0.66.
The survey?
The surveys, log survey CV. So that's a 50% increase in the log standard error of the survey index.
Like CV is.
The coastwide?
Sorry, 0.040. 0.066. Sorry.
I was gonna say, like, why even bother?
Just reading the 6 digits. Yeah, sorry.
Sorry. Oh,
No, it's still a small
this is-
value, but it
yeah.
has proportionally gone up.
these are definitely American problems. 0.04 to 0.06. And that's an order of magnitude smaller than the fishery. Fishery
The fishery CPU is quite tight. The fishery CPU itself is a naive index. It's just sum of effort over sum of catch, or vice versa. Remember, we had some discussions years ago about doing a more sophisticated approach, and we decided, based on some work that Cole Monahan did actually, that even though we could do a much more sophisticated standardization, he did a geostatistical model, a discretized GLIM, and compared to the raw index, and we got at that time, we got a pretty similar result. And the conclusion was keep it simple so you can explain it. But at that time, the CPUE wasn't having as big an effect on the models. Well, it's 4 o'clock.
Well, it's 4 o'clock. I think we'll probably wrap it up there for the day. Build up our appetites.
Yeah, I guess, yeah, the next, Dave's gone, so the next section is your drafting section, right?
From now until 5, theoretically.
So I don't know who has the control over the meeting, but I think we should say goodbye to the people online and close out for the day. We'll be planning to restart at 9 a.m. 9 a.m. tomorrow.
So I have a message from Dave. He said that the draft report has been sent to the SRB, so we should be able to continue with the place for today. Yeah, I think that's it for the meeting today. We can wrap up the online.
Yeah, I don't know who's running the
Click,
meeting.
click,
online.
push escape on that. And then you could probably at least mute the mic.
I don't have any. Oh,
You have the
yeah, I do.
mouse.
Sorry,
Yeah.
I have the mouse.
Just.
You guys